Hi everyone, so we're going to talk about distance of closest approach. So here we go. This is a nucleus, as you can see, nucleus of an atom. Okay, so let us say it has charge over it. It is positively charged. As you know, this is the nucleus, right? So it would be positively charged. Positively charged. And now this is an atom. Let's say the atom is Z. So the charge over it would be positive Ze. All right, so whatever the atomic number of this nucleus is, and the charge plus Ze. All right, and here, this, as you can see, this is an alpha particle over here. Okay, and you know that alpha particle, it has plus 2e charge over it. All right, it is a helium particle which has positive 2 charge over it. Okay, now let us say, let me just write it over here. Okay, so the charge over it has positive 2e charge over it, right? So this is the charge. All right, now this is moving. I threw a alpha particle, or I just say let's bombard a lot of alpha particles from an infinite distance. All right, so it's so much far from the nucleus of the atom, so it is at infinite distance, right? So which means that the radius, all right, that the distance between this alpha particle and this nucleus of the atom, it's infinite. Right, so it would be infinite. Right, so now this particle is moving with a velocity, let's say v alpha, and it has some mass which is m alpha. It is the mass. And v alpha, if I have to say what is v alpha is the velocity of alpha particle. You getting me? All right, now what will happen? Let's try to find potential energy at this point. Let us say this point, let me just mark it. Okay, so this point, let us say it is point O, right? So it is point O. At point O position, I'm trying to find the potential energy. Now we know that for the formula for finding potential energy, it is, I'm talking about magnitude, that's why I'm putting here this modulus. It is negative k Ze square upon r. So now as we know, r is infinite, so this can be, in comparison to infinite, this is nothing, the above value. So 1 upon infinite is just 0. You're going to break 1 into infinite parts, it's just 0. Right, it's just approximately equal to 0. So now potential energy's whole value you will be getting as 0. Alright, and for kinetic energy, as you know, kinetic energy formula half mv square. You know the mass of the particle, we just found out that the potential energy of this particle at this position is 0. Now let's find kinetic energy. So it will be half mv square. We know the mass of that particle is m alpha, and this is v alpha. I'm going to do the square of it. So this is the kinetic energy at this point, and this is the potential energy. Now let us just say that we just threw this alpha particle in the direction of the nucleus. All right, now what will happen? Now at some position, as you know, this is positively charged, it is positively charged, and this is also positively charged. At some position it will go with some speed, but it will start decreasing. The speed, the velocity, it will start decreasing, because this will exert a repulsion force. This is also positive. Let us say here is our alpha particle. Now this is positively charged, and this is also positively charged. As you can see, they will exert a repulsion force over each other. Repulsion will be there, so at certain position it will reach, and its velocity will become 0. You getting me or not? At some position the velocity of this particle will become 0 when it will be going near to the nucleus. All right, so its velocity will start decreasing, and at certain point it will reach that the velocity will become 0. And At the same time, you can find out the kinetic energy, and that will also be equal to 0 because it depends on velocity, and when velocity is 0, you definitely going to get kinetic energy is equal to 0, right? So now when kinetic energy is equal to 0, let's try to find potential energy at this point, right? So this is potential energy's formula, and for magnitude I'm putting here modulus, which will just just remove this negative sign. It would be k q1 q2 upon r. I told you about this formula in our first part of video where we were talking about the let me just say numerical extension of Rutherford's model. I told you that this is a formula for potential energy. Now what will happen, just put q1 here and q2, right? So you'll get it. This will be like this: potential energy and then negative k. This is the q1 here, q1 is this and q2 is this. All right, so let's say this is E and this is ZE, right? And on R, so it would be PE, which is potential energy. It would be equal to what? It would be equal to what? This is our potential energy. All right, now you should know this one thing, that by the conservation of energy, now kinetic energy at point O, as you know, at point O was 0, right? Wait, kinetic energy at point O when you found out, and the potential energy at point P. It's my bad, I just said kinetic energy at point O was 0. It was not 0. Potential energy was 0 at that point. Now it should be equal. I mean, you're getting 0, one of the energy 0 here and one of the energy 0 here, but you should know whatever the energy here is, the total energy, and the total energy here should remain equal by the conservation, by the law of conservation of energy. So which means that whatever the kinetic energy at point O was there, because potential energy here was definitely just 0, so we are not just counting that, and here kinetic energy was 0. Now it means that the kinetic energy at point O should be equal to potential energy at point P, right? Now let's try to write whatever we just found. Now we got that kinetic energy at point O was this much. All right, so this was the kinetic energy at this point, half m alpha v alpha n square. Now it should be equal to potential energy at point P, which is this negative kze square upon r, right? Wait, can we just go back? It is 2e. As you know, the charge over this alpha particle was 2e positive, so I forgot to write 2 over here. So 2e into ze, which will be 2 ze square k upon r. When I'm going to remove the modulus, there will be no negative sign. This was the value I was getting, so let's just write here like this. Now let's try to equate them and try to find the radius, because we are trying to find the closest distance, all right, the effective radius of nucleus. So what that is, it is just the distance between the nucleus of an atom and between this and the alpha particle, where that particle's velocity becomes 0. This is the distance. This is called that distance of closest approach, or effective radius of nucleus is the other name for that. Now let's try to simplify it. So it will get multiplied here, so it will be 1 to m alpha v alpha square upon k z e square into 2, right? Into 2 will be 1 upon r. So now r would be, that is radius, it will be 4kze square upon m alpha v alpha square. So this is the formula for this, topic, this concept for this topic just consisted of this derivation of this formula, distance of closest approach. Is it what we call, this is distance, this is that distance we were talking about. And here E is just the value of, just the charge over an electron, right? So it is 1.6 into 10 to the power minus 19 coulombs. And K is just a constant, its value is 9 into 10 to the power 9 Newton meter square, coulomb -2, coulomb to the power -2. And M alpha, it's just the mass of the alpha particle, which is 4 into 1.67 into 10 to the power -27 kgs. So this was all about it, and see you in our upcoming video. Well, I can summarize this for you once again. So we had an alpha particle, we threw it some velocity, and this velocity somehow at some position, due to some repulsion force, this became 0, and over that position we found out that the kinetic energy would eventually become 0 too. And here at the position point P, right here we got to know that the potential energy was 0, and here we're getting kinetic energy is equal to 0. Now to satisfy the conservation of energy, we knew that the total energy over here and the total energy over here, that should be equal, right? So we did the formula, we got we found out that whatever the kinetic energy over here at the alpha particle at point P was there, would be equal to the potential energy here at point O, at point P, let us say. So here potential energy was somehow, it was like this, it was this much, and they should be equal. So we try to put them equal, and we just simplified the equation, and this is what we got. This is the formula for finding that closest distance, or the the radius, effective radius of nucleus, means up to this extent. All right, up to this extent the nucleus has its power. All right, so yeah, this was the formula. You can just summarize it, just learn it. All right, no need for any derivation. You don't have to cram the derivation. It's not at all like that. You'll just need the formula, 4kze square divided by m alpha, which is the mass of alpha particle, and velocity of alpha square. Thanks, and we'll see you in our next upcoming video.